Now I'm going to do an additional case where, again, what we initially see as we look at this problem is not necessarily going to lend itself to techniques that we anticipate, but that we can figure out a way to get it into a form that we want. 3x squared minus 7x dx all over 3x plus 2. Now, this particular term, just like the last one I did, I got two terms in the bottom. I'm not particularly happy with that. But I look at this and I say, I've got a fraction whose denominator is a higher degree than its numerator. That means I can do long division here. And whatever I get as a result, those separate pieces, and one of them will have a remainder, that is then going to be what I'm going to do the integral of. So, long division here, I see 3x squared minus 7x divided by 3x plus 2. And it's okay, what do I need to multiply 3x by to get 3x squared? The answer is x. I put that in the x column here. X times 3x is 3x squared. X times 2 is 2x. I subtract. That goes away. Minus 7 minus 2 is minus 9x. And I ask myself the question, what do I need to multiply 3x by to get minus 9x? And the answer is minus 3. Minus 3, I put that in the ones column where there was nothing already. I get minus 9x. And I'm going to be subtracting this. And I get minus 6. And then I do the subtraction. First term goes away. Minus minus 6 becomes a 6. And that tells me that this fraction right here is equivalent to x minus 3 dx. Okay, because I said it's x minus 3. And there's a remainder here, which means there's an additional term that looks like this. 6 over 3x plus 2. Which is basically saying, okay, I get the 6. I can't divide any further because there's no x's in here, but I wish I could continue to divide. So this is what I would divide by, 6 over that, if I could keep going, and that's where the second term comes from. Now, once I have this integral, of course, the first one, this integrates to x squared over 2 minus 3x. That part's easy. The other part, so well, I would pull a 6 out, and then I would say, okay, I've got dx over 3x plus 2. And I would make the substitution and say, this looks like it may be of the form dx over du over u, natural log, but I need to make that substitution. U equals 3x plus 2. Du dx equals 3. Therefore, dx equals du over 3. And I make that substitution on that piece and say dx is du over 3. This is just u. I can pull the 3 out, and I'll have 6 over 3. Integral of du over u, which is 2 times the natural log of u, and u was just 3x plus 2. And so ultimately where I end up is here. And of course, all of these will throw a plus c on there. But that's what I get. I break it up as soon as I see higher degree on the top than on the bottom. I know that I can do long division and get a simplified version of what I need to do. One more case from this section. And that would be integral 3x plus 2 over the square root 1 minus x squared. Now, the cases that we looked at in section 7.6 and 7.5 and those kinds of cases, 7.7, were cases where we had a squared minus u squared. Well, we had that, and that's what we got here. However, typically we didn't have anything going on the top. However, when I look at this, I can say, well, anytime that I have a fraction, I can separate the fraction in two separate pieces, this over this, plus separately that over that. It's just kind of like if you go to the step, you've got a common denominator, but before you actually combine them together, they were separate fractions. So this can then be written as 3x over square root of 1 minus x squared plus, and this is dx, 2 over square root 1 minus x squared. Again, dx. Now, I look at these, and again, it's not immediately clear what I need to do. I look at those formulas, and this one looks to me to be of the form that, something over that, which is inverse sine. So that one looks like it's going to be inverse sine. All I really have to do there, the integral of this a squared minus u squared is inverse sine of a over u over a, sorry. And so u here is just x. I've got this extra 2, but the 2 I can pull outside anyway. And I say then this is precisely that form. This second term is going to become 2 times the inverse sine of x over 1, which is just inverse sine of x. The first one is a little bit more tricky. And I look at that and I say, well, I don't know what to do with that. However, I would say this. I'm going to start making a substitution, and I want to substitute the most complicated thing, right? So I'm going to let that thing be u. If u equals 1 minus x squared, du dx is minus 2x. That means that dx is du over minus 2x. So I'm going to try that substitution and see if it helps me. And sometimes it does and sometimes it doesn't. We don't know here. Okay, so what happens if I do that substitution? Then, of course, I start with this 3x on the top. I substitute for dx, du over minus 2x. And I have this square root of stuff, and that stuff is just u, so that is square root of u. The x's cancel. I now have some constants. I can bring that outside, and what do I have? Well, if I rewrite this in a different form, that's u to the minus 1/2 du. And u to the minus 1/2 du is of the form where I can raise the power by 1 and divide by it, which I do. I raise this power up by 1, it makes me u to the 1/2. I divide by 1/2 is the same as multiplying by 2. And those cancel, and I end up with minus 3. Now what is u? U is 1 minus x squared. So it is the square root of 1 minus x squared. That's what u to the 1/2 is. And that's the first term, and the second term is inverse sine of x. Of course, I can throw a plus c out there. So what 8.1 is really about is kind of summarizing all of these different techniques that we've developed so far. And there are more to be developed, but it's kind of taking a breath in somewhere deep into the book here and saying, there's a lot of ways that we know we recognize 20-some forms of different types of forms we want to get to. This is how to take something that you don't immediately recognize and massage it to get it into a form that it can fit precisely into one of those known forms.